Sometime in the next 24 to 36 months, we are going to run out of human words.
Literally.
Yeah, literally. We will have consumed basically every useful, high-quality sentence ever typed on the public internet. Welcome to the deep dive.
There's a very specific energy to working late into the night.
Oh, absolutely. The glow of the monitor, the rest of the world is asleep, and it is just you, your IDE, and a blinking cursor.
Right.
You are a software engineer. You spend your days and probably your nights building systems. You understand logic, architecture, dependency injection, and, well, the beautiful widget predictability of well-written code.
Tonight, we are going to look at something a little different.
Exactly. Tonight, we are turning down the lights and looking at the raw, chaotic fuel that is actually powering the biggest paradigm shift in our industry. We are talking about large language models.
But we aren't looking at the transformer architecture or, the attention mechanisms.
No, we are looking at the bedrock, the training data itself.
It really is the perfect late-night topic, I think. Because when you are building a standard enterprise application, you are usually querying a clean, normalized, well-documented relational database.
Yeah, you know exactly what schemas and data types to expect.
Exactly. But the AI models we are seeing today, the ones that are actively writing boilerplate code for you, drafting your emails, simulating complex reasoning.
They're definitely not built on clean databases.
No, they are built on a foundation that is incredibly messy, overwhelmingly vast, and entirely, unapologetically human.
Yeah, we're talking about billions and billions of scraped web pages. The entire AI revolution, basically everything we are marveling at right now, is fundamentally built on this massive, unfiltered snapshot of human existence online.
Which brings us back to the hook you mentioned at the top.
Right, the existential dread that is currently keeping AI researchers up at night. The fact that we are rapidly approaching a literal data wall.
It is a huge problem.
Okay, let's unpack this, because before we get to the impending scarcity of data, we have to start at the absolute beginning of the pipeline.
Because before you can curate or refine a model, you have to collect the raw data.
Right. And in this space, the granddaddy of all data sets is something called Common Crawl.
Common Crawl is the starting line. If you are training a foundational large language model today, this is your default starting point.
And it is incredibly important to understand that this isn't some secret proprietary vault locked away by a tech giant, right?
Not at all. It's a non-profit open repository. It is freely available to anyone.
We are talking about petabytes of web pages that have been continuously crawled, archived, and updated since 2007.
Petabytes of raw web data.
As a software engineer, let's just think about the sheer infrastructure required for that. You aren't just making a massive API call to some well-behaved endpoint.
Oh no, you are dealing with the open internet.
Yeah, you are dispatching crawlers to handle petabytes of unstructured asynchronous web requests. You are parsing deeply broken DOM trees.
Infinite redirect loops.
Yes, navigating expired SSL certificates and storing all of that chaos. And what you get back is a reflection of absolutely everything.
The good, the bad, and the very ugly.
Right. You get the brilliant, beautifully written, technical documentation from a specialized engineering blog, absolutely. But you also get the spam.
So much spam.
You get the 404 error pages, the broken HTML tags, the keyword-stuffed SEO marketing garbage, and, the endless forums of people arguing about entirely irrelevant things with terrible grammar.
And that sheer spectrum is basically the defining characteristic of Common Crawl.
Yeah.
When you have petabytes of scraped text, you are capturing the entire distribution of human communication. The statistically probable, the highly improbable, the eloquent, and the utterly incomprehensible.
It is raw statistical mass.
Exactly.
But wait, that is exactly where I want to push back for a second. As an engineer, the very first law of data processing is garbage in, garbage out.
Sure.
So if I ingest a data set that is 90% spam, broken HTML, and forum trolls, my output is going to be garbage.
That's a fair assumption.
If we are just scraping everything since 2007, isn't that an inherently toxic, noisy data set? How does a neural network learn anything remotely coherent, let alone how to write a syntactically correct Python script from petabytes of random, unfiltered internet chatter?
It is the fundamental paradox of early LLM training. But if we connect this to the bigger picture, you have to remember what the model is actually doing at this stage.
Okay, what is it doing?
It is not trying to learn truth or facts. It is simply trying to learn the statistical shape of language.
Right, just the syntax.
Yeah, Common Crawl provides the scale necessary to build the baseline probability distribution of tokens. It basically teaches the model the mathematical likelihood that the word "the" is followed by the word apple.
So it's pure unigram and bitagram probability at a massive scale. It's learning syntax by brute force exposure to volume.
Exactly. But to your point, if you stop there, if you just train a model on raw Common Crawl, you get a model that perfectly mimics the chaos of the internet.
Which is terrifying.
It is. It might spit out racist vitriol. It might try to sell you discount pharmaceuticals, and it certainly won't write clean Python code.
Right, so raw volume alone is totally insufficient for machine learning.
Right. The sheer scale of Common Crawl necessitates the absolute most crucial step in AI development, which is filtering and curation.
Because volume is just the raw material. It's the crude oil.
Yes, quality, utility, and reasoning require intentional refinement.
So we have this massive mile-wide net we've dragged across the bottom of the internet since 2007. We pull it up, and it's full of treasure, but it's mostly mud, old boots, and rusty cans.
That's a great visual.
The immediate engineering problem is sifting through that mud. And that shift in methodology brings us to a massive turning point in how researchers approach the signal-to-noise ratio.
You're talking about the pile.
Exactly. I'm talking about a landmark open-source project known as the pile.
The pile was an absolute revelation in the AI training space, because before the pile, the prevailing assumption was heavily skewed toward more is better.
Just feed the beast.
Right. If the model isn't smart enough, just throw more petabytes of raw text at the compute cluster. Scale was the only god.
But the researchers behind the pile demonstrated a totally different, highly deliberate philosophy.
They proved that the diversity and structure of the sources matter immensely. They didn't just dump the internet into a blender.
They created a highly curated training corpus using just 22 carefully chosen datasets.
Yes.
And here's where it gets really interesting to me. Because 22 datasets to a software engineer who is used to hearing about infinite scale, millions of rows, trillions of parameters.
That sounds like nothing.
It sounds tiny. It sounds like a weekend project.
Mm-hmm.
Why does carefully handpicking such a seemingly small number of data sets completely outperform just throwing more and more petabytes of raw, unfiltered text at the model?
It comes down to the principle of well-roundedness and the underlying structure of the data. Because when we say 22 data sets, we aren't talking about 22 simple text files.
All right.
We are talking about 22 massive, distinct categories of human knowledge. They included a subset of Common Crawl, yes, but they also explicitly included PubMed Central for dense medical literature,
Okay, wow.
GitHub for raw code, RSIF for academic math and physics papers, and FreeLaw for legal opinions.
So by intentionally selecting these diverse, highly structured sources, you are forcing the neural network to learn entirely different structures of logic.
Exactly.
I think I see where you're going with this. It's like cross-compiling your code for different operating systems.
Now, that's an interesting way to put it.
Yeah, like if you only ever write and test your application on one specific Linux distribution, it might run blazingly fast there. But the second you deploy it to a Windows environment or an ARM processor, it crashes because it relies on highly specific local assumptions.
That is an excellent way to frame it.
So mixing these 22 datasets is basically ensuring the model's core logic is truly robust across any environment.
Spot on. Because the language and logical structure used in a highly technical code base on GitHub is fundamentally different from the structure of a dense medical journal.
Which is different from a patent filing or a
Yeah.
screenplay.
Exactly. If you just rely on the raw internet, the model over-indexes on whatever is most statistically common, which is usually social media chatter and marketing copy.
Right.
By forcing the model to process these 22 distinct structures, you are building significantly better connective pathways. The weights inside the neural network become generalized rather than overfit to internet slang.
Wait, but if you're mixing 22 wildly distinct datasets into one massive training run, how does the model avoid context collision?
What do you mean?
How does it know when to use the software engineering definition of a bug versus the entomology definition of a bug if all this text is just mashed together in the latent space?
Ah, okay. That is where the transformer architecture truly shines in tandem with diverse data. Because the model isn't just storing definitions of individual words in isolation.
Right, the attention mechanism.
Yes. It is mapping words based on the tokens surrounding them. When it reads a GitHub repository, the token bug is surrounded by tokens like compile, error, and line.
And when it reads PubMed, bug is surrounded by infection, bacterial, and host.
Exactly. By giving it high-quality, dense examples of both, the model builds a highly multidimensional vector space. It literally learns to geometrically separate the contexts.
Wow.
That diversity creates a well-rounded intelligence rather than a narrow, fragile one that gets confused by a polysemy.
And when we talk about high quality, highly curated data that builds those robust vectors, there is one undisputed heavyweight champion of the world,
Oh, without a doubt.
the absolute gold standard for training data. According to the research notes we are looking at, Wikipedia is the highest value data source per token that exists anywhere on the internet.
It truly is the crown jewel of training data, and there are very specific architectural and linguistic reasons why Wikipedia provides such an outsized return on investment during training.
Let me guess, it comes down to information density.
That's a huge part of it, yes.
I think about it like this. If I go to a casual internet forum to learn about garbage collection in Java, I have to read through 100 tokens of people arguing, making typos, and posting memes just to find the actual technical explanation.
The signal-to-noise ratio is terrible.
Exactly. But Wikipedia is subject to strict editorial guidelines. It takes exactly 10 tokens to explain the same concept.
Right.
You aren't just feeding the model facts. You are mathematically training it on algorithmic efficiency. You're teaching the neural network how to compress thought.
That is exactly what is happening under the hood. Every single token in a Wikipedia article does heavy lifting. It is factual, neutral, and devoid of the emotional volatility and filler words you find in random internet forums.
It's just pure signal?
Yes. But beyond just the density, it is also incredibly well structured. Wikipedia has clear hierarchies, standardized headings, bulleted lists, and internal hyperlinking.
So it teaches the model how complex ideas are structurally broken down into subtopics.
Yes.
And crucially, it is freely available across hundreds of different languages, which I imagine is a massive advantage for the model's latent space.
The multilingual aspect is arguably its most powerful feature for foundational models.
Really? More than the density.
Yes, because Wikipedia is structured so consistently across languages, a model can learn a complex concept in English, map the structural understanding of that concept in its vector space, and then align it with the exact corresponding Wikipedia page in French or Japanese or Swahili.
Oh, wow. So it builds an underlying language-agnostic representation of reality.
Exactly. It learns that the concept of photosynthesis is a distinct mathematical cluster, regardless of which human language is being used to query it. When you measure the impact on a model's downstream performance per compute cycle, nothing else gives you the optimization that Wikipedia does.
Okay, so Wikipedia is this ultimate high-density fuel. The logical engineering step is obvious. Just feed the model 10 times more Wikipedia.
Sure, to scale it up.
Feed it 10 times more GitHub repositories and medical journals. But, we can't do that, can we?
No, we cannot.
Because we've already fed it all of it. We have consumed the entirety of the high-value data, which brings us crashing right into the problem researchers are calling the data wall.
Yes. The data wall is no longer a theoretical problem projected for the 2030s. It is a present-day, acute engineering crisis.
We are approaching the absolute mathematical limits of available high-quality text in the world.
Because human beings only type so fast, right?
Yeah.
And as a species, we only publish so many high-quality books, peer-reviewed articles, and well-documented code bases per year.
Yeah, and the AI models, driven by massive clusters of GPUs, are scaling up in their appetite for data exponentially faster than humanity can organically generate new high-quality information.
And to make matters infinitely more complicated for the engineers trying to train the next generation of models, the high-quality data that does exist is suddenly locked up in a massive legal minefield.
Right. As a software engineer listening to this, you know exactly what we're talking
Right.
about. The very code you write, the commits you push to public repositories, the architecture documentation you draft, all of it is suddenly the subject of intense, multi-billion-dollar scrutiny.
Because there are massive, ongoing legal battles right now over copyrighted books, news archives, and code bases being ingested as training data.
It is a massive clash of incentives playing out in real time.
Absolutely. On one side, you have independent developers, artists, and authors who are fiercely trying to protect their intellectual property and their livelihood.
And on the other side,
You have AI research labs arguing that ingesting data to train a neural network is functionally equivalent to a human reading a book to learn a style, which they argue falls strictly under fair use.
and the courts are actively deciding this right now, right?
Yes, and the jurisprudence is entirely unsettled.
And whatever the courts decide, it is going to actively reshape the data pipeline. Because if a judge rules tomorrow that you cannot use copyrighted books or specific open source code repositories without explicit paid licensing,
then a massive chunk of that high-quality, high-density data we just spent 10 minutes praising vanishes from the training pipeline overnight.
We hit the data wall even faster. The fuel supply just gets cut off.
Exactly.
So what does this all mean? If we are running out of high-quality human text, and the text we do have is locked up in an unpredictable legal battle, how do we keep building better models?
Well, the industry's current answer seems to be synthetic data.
Right, getting AI models to generate text and then using that AI-generated text to train the next generation of AI models.
Yeah.
But honestly, as a systems engineer, that sounds like a recipe for a catastrophic systemic bug. Isn't this just lossy compression, like saving a JPEG over and over again? Doesn't that risk a massive feedback loop where the data just degrades?
This raises an important question, and you have just identified the exact mathematical nightmare every data scientist is trying to solve right now.
Oh, great.
The formal term for the JPEG degradation you are describing is model collapse.
Model collapse. Okay, let's dig into the mechanics of that. How exactly does a model collapse?
It comes down to probability distributions. A large language model, by its very nature, favors high probability tokens. It wants to output the most expected, mathematically safe word.
Right.
When humans write, we naturally introduce variance. We use slang, we invent new metaphors, we make strange leaps of logic, we represent the long tail of the statistical distribution.
But an AI doesn't do that organically.
No. If you train an AI purely on the output of another AI over several generations, the model mathematically trims off that long tail. It clips the linguistic variance. It regresses entirely to the mean.
So the nuances of language start to degrade.
Exactly. The model begins to amplify its own safe, homogenized errors, and eventually it just spits out bland, repetitive, low-quality text. It is basically an algorithmic flattening of thought.
Wow, it's an echo chamber of the highest order. The edges blur, the contrast fades, and you are just left with a gray page.
That's a perfect way to describe it. But here's the reality of the industry. Because of the data wall and the legal lockup of human-generated content, going down the synthetic data route isn't just an experimental option anymore.
It's a strict necessity.
Yes. It forces the industry's hand. So the profound engineering challenge now is, how do you bypass model collapse? How do you create high-quality synthetic data?
Right, how do you program a neural network to generate training data that introduces enough artificial variance, logic, and complexity that the next model actually learns something net new rather than just eating its own tail?
It requires moving away from simple text generation and moving toward highly complex adversarial setups.
Adversarial setups.
Yeah, think of it structurally similar to a generative adversarial network, but applied to textual reasoning.
Okay, I'm with you.
You might have a generator model writing the synthetic textbook on quantum physics, and a separate discriminator model that has been trained strictly on high-quality human text, acting as an auditor.
Oh, so the discriminator tries to flag the synthetic data as fake or low variance?
Exactly. You force these models to compete, tweaking the reward systems until the generator produces text that is virtually indistinguishable from the unpredictability and nuance of human writing.
That's incredible.
We are moving from simply collecting scraped data to mathematically synthesizing cognitive variance.
It is a wild, almost philosophical shift in our industry. We are literally engineering synthetic human thought to feed the machines because we structurally ran out of the real thing.
It really is.
Okay, let's take a breath and recap the architecture of what we've covered tonight. We started in the wild west of Common Crawl, parsing broken DOM trees and dragging a massive net across petabytes of unfiltered internet noise since 2007.
Right.
We saw how researchers realized that statistical volume wasn't enough, leading to the highly curated cross-compiling refinement of the pile. We looked at the mathematical beauty of Wikipedia, acting as the ultimate high-density token source that teaches models how to compress thought.
A truly beautiful system.
And finally, we crash right into the impending data wall, where absolute scarcity and complex legal battles over IP are forcing engineers into the strange, uncharted territory of adversarial synthetic data generation.
It is a fascinating evolution of how we value information as a species.
Mm-hmm.
Data went from being something we just stored on servers to something we aggressively mined for analytics, and now
It's a scarce resource.
exactly. It is a scarce, finite resource that we have to artificially synthesize just to keep our systems scaling.
And all of that data, those trillions of carefully curated, heavily filtered, or adversarially synthesized tokens, they don't just exist in the ether. They don't run on magic.
They definitely do not.
They have to be mathematically processed. They require physical metal, silicon cooling systems, and massive amounts of electricity.
Mm.
So tomorrow, we are taking a hard pivot.
Looking forward to it.
We are shifting from the software and data pipeline directly into the physical hardware layer. We are going to explore how these massive data sets are actually crunched by the physical machines, the GPUs, the TPUs, and the massive warehouse-scale clusters of interconnected chips that do the actual heavy lifting of matrix multiplication.
The physical infrastructure, the networking, the memory bandwidth bottlenecks, the power distribution is just as complex and, frankly, just as legally and economically fraught as the data pipelines we discussed today.
It's going to be a great deep dive, but before we sign off and let you get back to your terminal, I want to leave you with something to ponder while you compile your code.
Always good to have a late-night thought experiment.
Exactly. If the future of large language models entirely relies on synthetic data to bypass these legal hurdles and hard data limits, how do we engineer systems to ensure future AI models don't lose the messy, unpredictable, and entirely organic nuance of human creativity?
It's the ultimate question.
Can we write an algorithm to preserve the very spark that made our data valuable in the first place? Keep coding, keep building, and we will see you tomorrow.